This is an exponential decay problem, and it's a really common type of problem, a half-life problem. So just in case you've never heard of half-life before, if you haven't taken Math 30, you've never heard of it, probably. Actually, I don't know, maybe in chemistry or something. But a half-life is basically means that when we're talking about especially radioactive materials, but also other things too, like fossils and stuff, a half-life means that the half-life is the amount of time it takes for half of the original amount to be remaining. So if I say the half-life is 50 years, that means after 50 years, there will be half of whatever was there before. Okay? So if I start at 100%, after 50 years, there'd be 50%. Then after another 50 years, there'd be 25%, because half of 50. Then another 50 years would be 12.5%, so forth. Okay? So here we're told that the half-life of some radioactive substance is 20 days, and there are 5 grams presently. So if I made like a table for this, I mean, we're going to talk about equations, but just imagine like simply, because sometimes the equations trick people up a little bit, but if we're just thinking of this, it means that after 0 days, there's 5 grams. After 20 days, there'd be 2.5. After 40 days, there'd be 1.25, and so forth. Okay, we just keep going. So after 60 days, there'd be half of 1.25, and so forth. You know, it just keeps going. That's how half-life works. So every that many days, there's half left. So the formula for this makes a lot of sense intuitively if you try to understand it. It's the amount, the final amount is equal to the initial amount times 1/2 to the power of time over half-life. Oops. Trying to like make my tea better. Okay, so time over half-life. So this makes sense because you think about like I'm going to take 5, which is my initial amount, and I'm going to take it times it by 1/2, and then this is the part where people usually forget. They're like they can't remember if it's multiplication or divide, and they're just trying to memorize it. But it makes sense. Like if you think about it, if it's been 60 days in total, if that's what your x value is, then 60 divided by 20 is 3, and it's being halved 3 times. Okay, that's what you're trying to think of. Like this entire exponent should be how many times it should be how many times it's going to be halved. So how many half-lives have there been? Okay, it makes a lot of sense. So here, when it asks when will there be only 1 gram remaining, okay, I know that my A naught is 5, because that's the initial amount. That's what the naught usually means initial, right? In like physics and in math, usually that little O means initial. Okay, then 1/2. And the half too, it makes sense as well, right? Like we talked about yesterday, if you're growing by 10%, it's 1 plus 10, right? And then you get 1.1. If it's shrinking by 50%, which is what's happening here, we're halving it. It's shrinking by 50%. Think of that as being 1 minus 0.5. Well, 1 minus 0.5 is 1/2. So that's why it's 1/2 here. Okay, and then t, which is time, over h, which is 20. So there's only one spot. I can't really get that, but that's okay. There's only one spot for the 1 to go. It's right there. Okay, so we're trying to figure out, on the other side here, so we're trying to figure out what is the value of t so that 5 times 1/2 to the power of t over 20 is equal to 1. Okay, that's what we're trying to figure out. Okay, so it's pretty straightforward, I think. Now here, there are a couple different ways to solve this. You would either have to do it using your graphing calculator. So if I gave you a graphing calculator, what would be the easiest way to solve this? If you had a calculator. No. Yeah. Okay, so don't just keep putting in values. That would take a long time, right? But any equation that you're given ever, if you have a graphing calculator, is solvable just using graphs. So if you put this into y1 and this into y2, or the other way around, it doesn't matter. You put one side of the equation into one graph, the other side of the equation into the other graph, and what do you find? Yeah, look for the intersect. Okay, and that will let you find the answer to any equation. Okay, so if you have your calculator, that's the way you do it. Now say you don't have your calculator. Okay, say your life has like gone into shambles and somehow you ended up in a scenario where you don't have a graphing calculator. I can't imagine that situation myself because I always have one. But if it did happen, okay, then what would you have to use? Someone who's taken Math 30. Logs. You would have to use logarithms. Okay, so that's what we're going to be spending most of our time today working on. I added a couple slides because I want to do a little more practice with logs than I usually do. In large part because some of the people in this room probably have never seen logs, and I feel bad for them because their life can't be full yet. Your life only really fills out once you've seen logs. Okay, so here, logs are, if you don't know, logs are the opposite of exponents. Okay, they're the inverse of exponents. The same way that like multiplication is the inverse of division, logs are the opposite of exponents. So we can use them to solve something when there's an x in the exponent. Okay, everyone with me so far? And I'm not actually going to show how to do it here because I want to go into some basic stuff first. Okay, so I added a couple slides, like I said. Yeah, I'll come. Okay. Oh, this is about E. This stuff about E later. I want to talk first about doing some log inverses. I'm going to go. So logs, okay, like I said, are the opposite of an exponent. So for instance, if you have something, let's do something really straightforward. If I had something like 5 to the power of x equals 25, okay, that one I assume could figure out. Okay, without needing logs. But logs is the opposite of this. So logs, what logs would be, the way I would write it is I would write log 525 equals x. These are inverses of each other. Okay, so the way that generally speaking you're taught it in Math 30 or whenever you learn logs is that the base stays the base and the other two switch. Okay, that's usually what's told to people. That's, for whatever reason, is confusing to people. Okay, so we'll see some other ways to talk about it. But before we even get into that too much, but I'll show you what I mean by that. Base stays base, the other two switch. The base of a power is the big number, right? Everyone's with me on that? So this here is the base of my power, the big number. It becomes the base of my logarithm. Maybe what's confusing is that the base of the logarithm is a little number. Okay, we're changing it up. So it becomes there, and then the other two switch sides. So 25 now, because it used to be on the other side of the equal sign, goes with the log, and the x goes on the other side. Okay, that's like the official rule. Now if you type this into your calculator, log 525, I'll teach you how if you don't know how already, it will give you the answer, which is 2. Okay? And clearly, if you looked at this, you would just know x was 2, but it would actually work. Now, what I want to get into here before we move on, because what I found last year with my 30-2 students is spending quite a bit of time on actually just evaluating logs. Seemed to help them. They got much better at logs than a lot of 30-1 students I've seen. So I was impressed with it, but it took a lot of practice. So looking at a log, I would like it if people were good enough at logs that they could just look at a simple log and evaluate it without a calculator. That is what I would like for you. Okay, so for instance, if you saw something like log 2, 8, and I'm not talking about really tricky ones, I'm talking about simple numbers, okay, I would like it if you could just look at that and tell me what the answer is. So can anyone tell me what the answer to, or the evaluation of log 2, 8 would be? 3. Okay, now, for those of you who maybe have never seen this, don't feel left out, okay, the way you're doing it, or you should be doing it, is you should be thinking 2 to the power of what? 2 to the power of what gives me 8. Okay, you're figuring out the exponent that would make that base into whatever the big number is. Okay, so here it's 3, because 2 cubed is 8. Okay, now let's look at slightly harder, but not significantly harder. If you have ones that are fractions, okay, so say I had something like, my gosh, what's happening here? Okay, log 2, 1 over 16. Does anyone have an idea of what that one would be? -4. Thank you, Cash. Okay, so fractions, all you have to remember is that negative exponents make fractions. Okay, negative exponents make the number go in the bottom. So you're like, well, 2 to the power of what is 16? It's 4. Okay, and since it's 1 over 16, it's -4. Is everyone okay with that? It's good so far? Okay. So far, so good. Hey, what about something like this? One half. Thank you, Cash. A Cash is the best at logs.
Am I actually that dumb? I thought you were trying to use 2.
Okay, so fractions, similarly, okay, an exponent with a fraction is the same as a root. So if you have x to the power of 1/2, that's the same as square root of x. Okay, if you have x to the 1/3, that's the same as the cube root of x. So here, what you should be looking at is, well, okay, I know that 8 is the square root of 64, so that would be a square root, which is a half. Okay, that's the way you should be thinking about these things. So what I'm going to do right now is I'm just going to order here, because I really just want to focus on logs first. Okay, so yeah, just like our crappy school internet. So just like that power law, once it catches up, if it ever does, okay, a to the x times a to the y is equal to a to the x plus y. We have logs. Logs, the rules are that if you have a log with a multiplication, it's like literally the opposite. If there's a multiplication, you can split it up into 2 logs that are adding. So it's like the opposite. Before, when you had 2 multiplications, you could put it together to add. Here, if you have them adding, you can put them together to multiply. They're just inverse rules of one another. And it's the same with the other rules. They're all really important, and I'll show you how to work with them. Maybe if I close out of here. Okay. Okay, so if we look at, there's 3 rules. Okay, there's the adding rule, that when you add, you multiply. There's the power rule, okay, which is that when you have something to a power, you can drop it down to the front. That's a really important rule. Okay, let's see. Yeah, I think that maybe helped to catch up a little bit. Okay, so that middle rule, no, it's still lagging. Okay, so in the middle here, this rule is really important. When you have this power out here, you can drop it down to the front. Okay, and then finally, when it's a division, you subtract. So it's very, very similar to the power laws. I'm going to show you how I want you to use them here for this next question. Okay, well, either way, here it is. I swear I put this in here earlier. I guess not. Okay. Here. Oh, it's not up yet because it's really lagging. Maybe I'll just do it on the screen. But then you won't be able to watch it later. I'll do this one. Okay. So I'm just going to do this example with you guys about how to use these laws. Okay, so this is the way I want you to use these laws. These questions are also really common in Math 30, at least on the departmental they are. They really like them. It's them wanting you to just use these laws to like rewrite logarithms in terms of other variables. So here we have that a is log x, b is log y, and c is log z. Write the following expressions in terms of a, b, and c. So what you want to do here is you want to split these things up, and we jumped right into hard ones. I'm not doing really simple ones. But when there's a multiplication, the way you split them up is by adding. And when there's a division, the way you split them up is by subtracting. So don't overcomplicate it here. I can split this one up. That's log x squared y z cubed. I can split, that's a 3-way multiplication. So I can split it up into 3 additions. So I can split it up into log x squared plus log y plus log z cubed, like that. Okay, I can split it up like that. So once I split it up like that, now this is where I think most people make mistakes, is people are like, oh, okay, well that's a squared, b, and c cubed. But it's not, because this is not log x squared. Like there's no brackets, right? Like there's no, it's not like that. It's not log x squared. That's what a squared would look like. Okay? It's log of x squared. The brackets would not go around log x. The brackets would have to go, if you were going to use brackets, would go around x squared. Okay? So there's a difference, and they didn't appear there until just now, but now you can see what I mean. Okay? Those brackets would not be around log x. They would be around x squared, if anything. So the way that we have to simplify this is before we deal with, put the a's and the b's in, we have to deal with these powers. So the power rule, the middle rule from the last slide, is that this 2 can move down to the front, right? So instead, I can write that, and I wouldn't necessarily expect you to write down all these steps, but you write down 2 log x plus log y plus, what would the last part be? 3 log z. Okay, and then that, now I can replace my things. So instead of 2 log x, I can write 2a. Instead of log y, I can write b. And instead of 3 log z, I can write 3c. Okay, and it's eventually going to come up, I'm sure. Okay, one day. Okay, I'm going to do the second one. That these rules work in conjunction together. Okay. Man, I'm all out of order here. Thought I put that